In this video, we're going to talk about the graph of a rational function. So here is the outline of the major steps to analyzing the graph of a rational function, whether you are taking the function and graphing it or working backwards from a graph. So here are the steps that I think are important. So I would definitely factor the numerator and denominator if they're not already in simplest form. Get it down to lowest terms, find the intercepts, the x and the y-intercepts if they exist, find the vertical asymptotes, find the horizontal or oblique asymptote if they exist, and then from there you're just figuring out what behavior the graph will have between those asymptotes, between those intercepts. Does it go up, does it go down from the x-axis? And there's some more steps there that the book thinks important, but you know, I think we can get away with just these 6. So let's give it a shot. All right, here's our first function. So we have x minus 1 over x squared minus 4. The only thing I need to factor is the denominator. All right, so the denominator becomes x plus 2, x minus 2, pretty standard. I don't have any holes because I don't have the same factor on top and bottom. Looks like I've got one x-intercept, right, because we set that equal to 0. That'll give me the x-intercept, and then I'll have 2 vertical asymptotes. So, got it factored, have the x-intercept, x minus 1 is equal to 0, so my x-intercept's at 1. Y-intercept is at x is equal to 0, so I plug in a 0 here, 0 there. Essentially, it's all the constants simplified. So that's negative 1 over negative 4, so that's at 1/4. We know our vertical asymptotes are at negative 2 and positive 2. And then the other thing I can find is the horizontal asymptote. So my n value is 1, my m value is 2, so that means top is less than the bottom, so my horizontal asymptote is at y equals 0. Let's put those things on a graph and see what we get. So I put in all my asymptotes, and here's how you label them. You label them as if they were a vertical or horizontal line. It doesn't matter if it goes on the top or the bottom or the whatever side, doesn't matter. Just make sure you label them. Most asymptotes are graphed in red. It's pretty standard, but you can graph it in whatever color you want. And I have my x and my y-intercepts. So what I'm thinking is that over here, the function's either going to exist up here or down here. And then here, it's probably going to curve down like this. And then same deal over here as we had over here. It's either going to be up here or down here. So what I like to do is throw in some of these x values. So I might make a table with negative 4, negative 3, negative 1, and 3 and 4. So all I did was pick those numbers that I mentioned and then just plug them into the function, and I got their approximate. So you could plug in any numbers you want. You can keep going, you can go big, you can go small, doesn't matter. We're just trying to find where the curves will exist. So I plotted as best as I could on my iPad here. And so I've got these 2 points which tell me that this thing is going to curve like this. So it's not going to interact with either of these asymptotes, so it's going to curve like that. This guy is definitely going to curve like this, and this guy looks to be going up like that. So let's connect them. I'm so good at connecting points to make a curve. This ain't pretty, but here's what we got. We got this curve going down here, we got this guy, and we got that guy. And here's a much prettier version of what the graph actually looks like. And let's replicate those same steps, but with a new function. So we've got x squared minus 1 over x. So the first thing I'm going to do is factor it and see what I can find out. Okay, in factored form, x squared minus 1 becomes x plus 1, x minus 1. Forgive my handwriting there. Forgive all my handwriting. Divided by x. So my x-intercepts are going to be negative 1 and positive 1. My y-intercept, so when I plug in 0 for x, that zeroes this out and that out. So I just get negative 1 over 0. So there's no y-intercept. This function doesn't cross the y-axis. And my vertical asymptote is x is equal to 0. And for horizontal, I've got a 2 over 1. So n is 2, m is 1. That is, n is greater than m by 1, so I have to divide. And when I do that, I find my equation x plus 0, or y is equal to x. So that's going to be my oblique asymptote. Let's graph those things and see what we got. So my 2 asymptotes, x is equal to 0, and then y is equal to x, is this kind of it's kind of a line. And then I've got my two x-intercepts here. Again, there's no y-intercept because there's a vertical asymptote there. So I'm going to make my table of values with some values over here and some values over here and see where this is going to go. So putting in two numbers to the left and two numbers to the right of the asymptotes that we know, plugging it into this function, I get approximate points. So these points exist down over here, so that tells me the curve is going to curve around our asymptotes like this, and then over here I get curves over this way. I know I'm not going to have a function up here or down here. Those numbers just didn't pan out. And a much better looking graph than this one. All right, and you know the drill by now. Let's do the same steps, but with this new function here. So I've got a quadratic on top and bottom, gonna factor both. Let's see what happens. All right, so when I factor this, I get 2x minus 1, x minus 2 on the top, and x plus 2 and x minus 2 on the bottom. Immediately I see that I've got the same factor and x minus 2 on top and bottom. So setting that equal to 0, I have a hole at x equals 2. So I plug 2 into the remaining x's here, right? Because if I plugged it in there, it would zero out the whole thing, which defeats the purpose. So I plug that in and I get 3/4. So the hole is at 2 comma 3/4, which we'll graph eventually. So the remaining top factor is going to give me my x-intercept at 1/2. I plug in 0 for x, which is 2 over -4. That's -1/2. That's my y-intercept. My vertical asymptote is my remaining denominator factor here, so that's at x is equal to -2. And my n over m, they're the same degree, 2 over 2. So that gives me y equals 2 over 1 or y equals 2 as my horizontal asymptote. So let's figure these out on the graph. All right, asymptotes are in, hole is right here, my two intercepts are right here. So that pretty much tells me that I'm going to have a curve that goes up like this. We can definitely check -1 and maybe 3, and then I have a feeling that the rest of the function will go here, but it could also go here. So let's plug in some numbers and see. All right, plugging in my values into this function, totally used the table feature of my graphing calculator because I didn't feel like typing these in individually, so that's why we just have answers here. So over here it looks like this curve is going to exist up here like I thought, and then -1 is definitely down here, so it definitely curves up like that because 3 is also up there. So let's connect it. So here's my interpretive version, and here's the books, which looks so much better, but you know, you get the idea. And let's do one last example, but this time let's flip the script and start with the graph and work backwards to the equation. So I'm going to analyze this whole function for everything I did before. Intercepts, asymptotes, holes, anything else that I can find. And let's see what we've got. All right, so what do I have? I've got two x-intercepts. I've got one at -2 and it bounces. So I'm thinking that might have a multiplicity of 2, like x plus 2 all squared, perhaps. And then there's also an x-intercept at 5, and that crosses, so that's probably a multiplicity of 1. Got a y-intercept at -2, don't have to worry about multiplicities. I've got two vertical asymptotes. I'm going to have at least two factors on the bottom, -5, +2. And I've got a horizontal at y equals 2, which is the a over b thing, so that tells me that the degree on the top is the same as the degree on the bottom. So let's try to put together what we have. All right, here's what I've got. So because of the horizontal asymptote being 2, I'm thinking it might be 2 over 1 here, right? Because we've got the same power on top and bottom. It's a over b. A over b is probably 2 over 1. And then I put in my x-intercepts, x plus 2 squared, right, because it bounces, and then x minus 5, and it crosses, and then my two horizontal asymptotes, so that 1 coming from 2 over 1. So x plus 5, x minus 2. Now, I've got it in balance. I'm missing something. So I've got 2 plus 1, a third degree on the top. I've got 1 plus 1, which is 2 on the bottom. That won't create this horizontal asymptote. Plus, I can check using the y-intercept. So if I plug in 0 for all of my x's, that should give me -2. Let's see what we get when I plug in all the zeros for x when I have just what I have here. Let's just see. Okay, I plugged in zeros for all the x's of what I have right now. So that's 2 times 0 plus 2 squared, so that's 2 squared, yada yada, times negative 5 over 1, 5 times negative 2. That's negative 40 over negative 10, which is positive 4. So, right, if I plug in 0 for x, that gives me my y-intercept. This has a y-intercept of 4, which is not the y-intercept of our graph. So how can I manipulate the bottom? I have to square something on the bottom, right? Because I have a degree of 3 and a degree of 2, and they need to match. I'm not going to add 1 to the top. That doesn't make sense. Because I would need to then add 2 to the bottom, and I'm not about to do that. So either got to square the 5 or square the negative 2. So this is a negative on the bottom. Which I want to be positive, because a negative divided by a positive would give me a negative. So let's try to square the negative 2. Let's see what happens. I think we did it. So squaring that on the bottom makes negative 2 squared, which is 4 times 5, which is 20. And negative 40 divided by 20 is negative 2, which is our y-intercept, which means this is a function that represents this graph. Woo. This is definitely how I feel after solving that last problem. In other words, thank you. Thank you so much for watching.